Welcome back to Physics, Uniform Circular Motion, Part 3. Part 3, we're going to go do some more example problems, but we're going to do two more example problems. These ones are a little more down to earth, except for the last one. Last one, we're going to actually go up in orbit. I want to show you a really cool example of that. We're going to talk about future space stations. All right. This normally would be a lab that we would do in class. So it's kind of good that we're going to go over this together. Feel free to do this at home. Just make sure there's no one in the area. You don't whack anybody in the head. What we're going to do is we're going to take a piece of string, and you're going to hold on to one end of the string. And on the end of that string, you're going to put some sort of a mass. Something preferably that won't come flying off. Okay? Now, the student just keeps on swinging this thing around and around and around and around in a circle over their head. Okay? So, a student is swinging a 0.100 kilogram. That's a 100 gram mass, or a 0.001 kilogram mass around their head, in other words over their head, at the end of a string, and the string is 1.3 meters long. And every time they spin that thing around in circles, it takes 0.3 seconds to complete one time around the circle. Okay, it takes 0.3 seconds to complete one time around the circle. So let's write down a couple of things that we know. First thing we know is that radius right there. That is 1.30 meters. And that 0.300 seconds, that is the period. So 0.300 seconds, that's going to be the period. And that 0.100 kilograms, that's going to be our mass, which we'll probably need later when we calculate the force. All right, first part of the question asks, calculate the tangential velocity of the mass. Calculate the tangential velocity of the mass. So we'll bring up our tangential velocity formula, 2 pi r over the period. Now we start plugging in the numbers. Tangential velocity is 2 times pi times the radius, which we said is 1.30. All that's divided by the period, which is 0.300. Now, if you multiply that all the way across, I got 27.2 meters per second. Okay? So in other words, if that string were to suddenly break, then this object is going to take off at a tangent, and its velocity going off in that new direction, obeying Newton's first law, is going to be 27.2 meters per second. Part B. They want us to calculate the centripetal acceleration. The centripetal acceleration is the tangential velocity squared divided by the radius. So, the tangential velocity we just found, 27.2 squared, divided by the radius, again, which is 1.3. And if you do that, you get 569 meters per second squared. Now, that may not impress you a whole lot, but let me do a little sidestep here to give you some appreciation. Use the color you can read here. What is gravity? Gravity, of course, every time you fall and hit the ground, you just experienced 1g. Okay? 1g is 9.8 meters per second squared. This poor ball, whatever you got on the end of the string here, is experiencing 569 meters per second squared. When you fall, you experience 9.8 meters per second squared. When you go on an amusement park ride, you might experience 2 or 3 G's. This poor little ball or mass flying around in circles is going to experience 596 meters per second squared. So something cool is like if you hear pilots and they talk about flying around the jets and they experience 12 G's or 10 G's, what you do is you take your acceleration which is 569, and you divide it by gravity, which is 9.8. It gives you how many gravities it's experiencing. And this poor little thing, if you got 596 divided by 9.8, that means that little mass slinging around the circle there is going to experience just over 58 G's. Ouch. Something a human body cannot do. Okay, onward and upward. Now they want us to calculate the centripetal force acting on that mass. So the centripetal force is just the mass times the centripetal acceleration. So we're going to take that mass, which we haven't needed until now, 0.1. So this is 0.1 times the centripetal acceleration we just found, 569. And you multiply those out, you'll get 56.9 newtons. Okay, 56.9 newtons. Now, the last little question here is just to make sure you understand. They're asking, what is acting as the centripetal force on the mass? In other words, this mass keeps on going around in circles, because there's a centripetal force pulling on it. Well, what's doing the pulling? What's pulling on the object? If you look at the picture, of course, it's got to be that string right there. So the answer to that question is, what is acting as a centripetal force on the mass? It is the string. As we learned some time back, anytime you got a force that goes through a string, a rope, a chain, or a cable, that's called a tension force. So I'll put force, the little T for tension force, and we'll write down tension. Okay, it's a tension force. Now, the next example is just cool. I've been dying to show you this one. I think it's the coolest thing ever. Getting all futuristic here. I wish I could zoom in a little bit farther there, but that's it. This is a picture, an artist's concept drawing of a space station in orbit or going around outer space. It looks like a really large metallic donut, and inside that donut structure is living quarters and places where to do your experiments and everything else you're supposed to do when you're in outer space. Now, the uniqueness about this is if you go back to some amusement park rides where they spin you around in circles really fast and you stick to the outside walls. If you think about it, you could, if that thing was spinning fast enough, you could basically stand up sideways on the inside of that. And that's the idea of this circular ring on this space station going around circles. Once it gets up in orbit, it's up there, you get this thing starting to spin. You get it spinning just strong enough, and of course everything wants to kind of collect to the outside ring, kind of creates an artificial gravity. It's not real gravity, but it simulates gravity. So I don't know if you can see this, but here's someone else's simpler sketch right here. I'll try and hold that up a little closer to the camera. They show an example of, let's say you look at a breakaway. There's somebody just standing there. It looks like they're standing on the outside of the donut out here. From the inside, but they're standing inside there. And the cool part about that, of course, the reason why we want to do that is we have figured out by putting putting astronauts in outer space, without the pull of gravity, their hearts don't have to work as hard to pump blood. So the normal astronaut's heart will shrink by 10% because it doesn't have to work as hard. So we have to make them exercise and stress their hearts out a little bit to keep them built up and keep them strong. If we were to create a space station like this donut ring shape and we got it spinning, well, then everybody would stick to the outside basically, and they could walk around the outside or the inside of this ring, but on the outside ring part. Of course, we create floors in there. I'll show you a really amazing artist view of this thing. Let me, there's a lot of detail. You should look this up if you get a chance online. This is an artist's rendition of a gigantic version of it where you've got entire cities or neighborhoods inside that ring, creating an artificial environment. And notice that everybody is slung to the outside, creating that artificial gravity to the outside of the donut ring, which is just cool. Okay? It's a very cheap, easy way to provide artificial gravity for our spacemen so they won't have to have any health problems or health issues. So what we're going to do is we're going to do a calculation for this. It's like a little challenge problem. And the question is, if the basic radius of a space station is 500 meters, okay, so the radius is 500 meters of this big donut, at what tangential velocity will the ring space station have to be rotated in order to create an artificial gravity acceleration of 9.8 meters per second squared? In other words, the centripetal acceleration. So in other words, once you get this space station up there, you get everybody to sit down, you get this thing spinning around in circles, you get it at the right speed, everybody gets out of their seats, they start walking around the inside of that thing, and everybody's just like they've got gravity. Okay? So what we got to do is if we've got a space station that's 500 meters in radius, how fast do we need to get it so that they feel an acceleration, a centripetal acceleration of 9.8, so it matches gravity? So what are we looking for? They want us to know or find out what the tangential velocity is. They have told us what the centripetal acceleration is. They want it to be equal to gravity, which is 9.8. And they told us the radius is 500 meters. So which formula are we going to use? Which of the three? Which of the three has a radius, has a centripetal acceleration, and has the tangential velocity? And of course, I think it's the formula for centripetal acceleration. Centripetal acceleration is the tangential velocity squared divided by the radius. The centripetal acceleration, we're going to set that at gravity for Earth, 9.80. The tangential velocity is what we got to find. Be careful, that's squared. And the radius is 500 meters. So if we very carefully calculate this out, and don't forget to take the square root at the end because of that square right there, you're going to get a tangential velocity of 70 meters per second. 70 meters per second. Now, 70 meters per second. Can you think, I mean, how fast is that? How about miles per hour? What does that actually mean? Well, I did the conversion for us. 70 meters per second is actually 157 miles per hour. Holy smokes. That thing is going to be really spinning fast. Okay, 157 meters per second. So now if you're interested in getting into designing spacecrafts and space stations, you may want to think about, well, how are we going to get that thing to spin that fast? And if everybody looks out these windows over here, and they can see stars and the moon and everybody else and other planets around there, this thing's still going to be cooking around so fast. I mean, are they going to get dizzy feeling? You know, it's hard to tell. So, some good questions you may want to think about is what would happen if we took the radius of the space station right here, instead of making it 500, would it be better if I made it 1,000, made it bigger? Or would it be better if I made it smaller? What would be a really good radius to have so that this thing isn't spinning around making everybody dizzy, but it still provides gravity? Okay, that's the end of video number 3. Hope you've had some fun seeing some application problems. If you have any questions, be sure to email me. I'll talk to you later.